Okay, physical science time today. Today is the good day. Today is one of the days we love. Today we are talking about waves. Some can say waves, yeah. I don't know who would do that, but it has been said. Waves. Waves is such a beautiful topic in science for us to take notes over. That we should have our notes out for. That we could even, if we had to, we could borrow some paper from one of our friends and a pencil and take it. Yeah.
She does have paper.
She does.
Wow.
A wave. Lucas, let's pay attention, best friend. A wave is one of the fundamental ways of thinking about things in science that you should understand. Let me put this in purple. All energy disturbances are waves. What that means, let's talk a little bit about that. But a disturbance, I don't know, that could probably maybe have found a better word, but at the top of my head, that's what I came up with. But a disturbance is we could put like oscillation or vibration, but it's maybe displacement would be a better word. It's some change, because remember, one of our most basic concepts in all of science is that energy is the ability to cause change. So it's some change in the way a particular structure is. And that, when that repeats, we call that a wave. Did you hear when I did that with my coffee? It's a wave. Yeah, energy is change. Energy in science, everything that has ever changed or will ever change does so because of energy. Energy is the quantity by which we measure the amount of change. And in various circumstances, in fact, in most circumstances, that change takes the place of a repeating oscillation, vibration, displacement. Those are just different words. I'm trying to orbit the correct thing. None of those is fully satisfying me, but let's draw a wave. Why don't you draw a wave first, and then I'll draw a wave after, and I'll check yours. Will you just draw a wave? Just do it. Just do it. And let's try to relate this to your little lives. If you drew something like this, that's what I was expecting. Did anyone not draw something like that? That's probably what you got. And now, I want you to consider that maybe this could be a lot of different things, the way we have drawn this, right? Maybe this is your sleep-wake cycle, right? Like here, you're awake, here you're asleep. Awake, asleep, awake, asleep. Maybe, like Eliana's, what'd you do with your flowers, bud? Okay, Eliana's flowers, which are outside, maybe you saw them, but Eliana brought flowers. They were alive yesterday, weren't they, Eliana? And then today they are dead, dying. Alive, dead, alive, dead, alive, dead. And this, this is not going to become a reincarnation podcast. I'm not talking about like you're alive and then you die and then you're alive again in the way that you might be expecting. But in general, things are living things, and then there are dead things. And then those dead things lead to living things. Are you following me a little bit? Like, I was just telling Mr. O in the hall, because of Eliana's dead flowers, without death, there is not life. Without that, there is some rich organic matter in the soil, nothing will grow, right? That's what soil fertility is. If you're a farmer, raise your hand if you have ever been associated with farming in your life. Of course, you're in Crawford, so you all have. And even if you don't think you have, because you're a city slicker, you have eaten food, and so you are associated with farming. But the soil that grows food, the soil is made of dead stuff. This cycle of live, dead, alive, dead, alive, dead, or day, night, day, night, day, night, or good day, bad day, right? You ever have a good day?
No.
Yes, when you dress up in the morning, you woke up at 7:46 instead of 7:48, you have time to get dressed up. You're having a good day. That's every day. Some days you drop your backpack in the mud puddle. I don't know what your life is like. Maybe some days you're Your phone gets dropped in the hallway and it breaks into a million pieces because it fell out of your backpack. Bad day. But there's this cycle. And the point I'm trying to make, it's not always Monday, good day, Tuesday, bad day, Wednesday, good day, Thursday, bad day. Obviously, it isn't one-to-one like that. But the point I'm trying to make is it never goes like this. Like a wave does not just, here's the hope I'm trying to give you. If you're in a bad day, there will be a good day again. And if you're in a good day, there will be a bad day again. That's life. There is never, a wave is not this. This is not a wave. A wave, you can't have a wave that is all crest and no trough. That has never happened in the history of the universe. The philosophical point is that you can never have a life that is all good days, because then a good day means nothing. You can't have a high without a low. And it's the same with a wave. This is the crest of a wave. This is the trough of a wave. Trough is T-R-U-G-H. I guess I did make my G and my H almost identical. This little brown thing that I've drawn is called the baseline. I think your book calls it the baseline. Is that correct? Maybe it calls it the midpoint. The rest position. Your book calls it a rest position. Other books have called it a baseline. And now these are the measurements that we take of waves. What you should notice from your vocab, what do we call the distance from one crest to another? Or it could also be from one trough to another, and these are either one of them called the wavelength, and that is abbreviated with the Greek letter lambda. This is lambda, and that stands for wavelength. How do you think we would measure wavelengths? Well, it's a length, so what do we use to measure length in the SI? Meters or some derivative thereof. Wavelength is measured in meters. Now, what about this one? This distance from the height of the crest to the midline or the bottom of the... What do you call that? What do you call the distance from the midline to the trough? Amplitude. Yep. Okay. And then the other thing that we measure about it is how many of these waves will pass in a given amount of time is called the frequency, which we usually in science use with the Greek letter nu. Oops, I just drew it wrong. I just wrote the letter J in English, or Latin, I guess. This is the Greek letter nu, and that is the frequency. I think your book, and I think probably if you were to take a test, would use the lowercase letter f, and that is measured in hertz, which is 1/seconds. So that's how many pass in a given amount of time. So like if we had 3 waves pass in a second, we would say that wave has a frequency of 3 hertz. If we had a million waves pass in a second, we would say that frequency was 1,000,000 hertz or a megahertz. You remember how those prefixes work. So those are the basics of a wave. And with those, we have this equation. The velocity of a wave is equal to its frequency times its wavelength, where v is velocity, nu is frequency, and lambda is wavelength. What do we measure wavelength in? Again, meters. Frequency, hertz. Remember that a hertz is a 1/second. So if we have meters multiplied by 1/seconds, what is our velocity going to be measured in? Meters, look at this little equation in your head. Meters times 1/second. What's my new unit going to be? Meter over second. Does it make sense for that to be a velocity? Well, yeah, that's what we've been measuring velocity in all year long. And using this equation, we can determine, given the,
What's the upside down line?
Lambda is wavelength. Can you not see past my podium? I'll move it for you. This kind of wave is usually called a transverse wave when we've diagrammed it like this. Let me give you a demonstration here. the two main kinds of wave are the one that I've diagrammed up there, where a wave is energy, right? A wave is a manifestation of energy. I've said that already. The energy is what is flowing from place to place in a wave. Let me hook this onto here and hopefully not break my television set. Someone say a little prayer for the television set. Someone say a prayer for my coffee. Energy is what is moving. I mean, I don't know. Energy is what's flowing in a wave. The matter itself does not move from place to place. So you think of an ocean wave, right? That's the kind of wave that most of us are familiar with. Well, maybe not most of us because we don't live by the ocean, but we're aware of the existence of waves in the ocean, yeah? But a very common misconception is that people think that the wave moves stuff from place to place. Have you ever experienced waves at all? Because like Whitney Lake and Box Butte those don't have waves really, not in any real way. A wave pool, yeah. So if you're swimming in the wave pool, do the waves push you away? Like if the waves are emanating from a source over here, do you get pushed by them to the shore? You don't. You're wrong, you don't. Do you get sucked in towards the waves? Not generally, nope. What if you look out at a wave pool, if I thought about that example, I would have showed you a video. What are the people, every single person in the wave pool is screaming, but they're also doing what? Jumping. No, they're not jumping, they're in the water. Woo! Yeah, yes, okay, I guess. They're moving up and down. Every single person is just moving up and down. Some of them, you can swim still, just like you can if there's no waves. So some of them are going up and down with the waves, but also swimming. But that's from their own power. Some of them, if they jumped into the wave pool, maybe they still have some momentum from that jump. But most people, the motion that the wave is actually causing them to do is just up and down. Energy flows, not matter. The matter does not move from place to place. Let me show you in real life an example of this. I have my spring coil thing of science, which I will first knock down. This is part of the plan. I'm not an idiot. Stay on there. Don't make a fool out of me again. So here I have my energy coil of science. And you can see, let's maybe, I'm trying to pick something the camera can pick up. I'll color, blue maybe is not the best color for this. Can you see, the camera may not ever be able to see this, but can you see these two that I'm coloring blue here and also getting it all over my hand? Yeah. You can kind of see them. Can the camera pick that up one single bit? Yes, it can. Okay, so that's good. Woo! Is the blue thing going from my hand to the TV or back or the other way? What's the blue thing doing? Just focus on the blue. The blue is... Okay, well, imagine you can see it. It's staying put. It's moving up and down in place, though, right? It's vibrating or oscillating. It's being displaced. That's a transverse wave. When the energy is flowing from my hand to the television set, but the wave itself is moving perpendicular to that, it's called transverse. Okay, you should write that down. I'm not in a position to write it now. But transverse is when the particles oscillate or the particles vibrate perpendicular to the energy flow. Particles vibrate perpendicular to the energy flow. Perpendicular meaning like the energy, again, moving this direction from my hand to the TV, but the energy is flowing, or sorry, the matter is moving up and down. That's perpendicular. Do you see? If I do it this way, that's perpendicular too. There are two directions of perpendicularity because it's in 3 dimensions. So both of those are transverse waves. Now I can do the other kind is called a longitudinal wave. Focus on this little blue guy. You see him there? Right by my thumb. You see him? That's a wave too. In the case of a longitudinal wave, the matter is oscillating, vibrating in the same direction as the energy flow. So it's going back and forth, we might say. That's a longitudinal wave. Do you see it? How do these blue things move? I could have died. That didn't hit me at all, but I could have died. That would have been, let me make this clear. If I ever am taking a video and I die, stop the recording and then post it on YouTube. Yeah. I'll write these down now, but yeah. So try to remember the actions I did while we're writing these down. I'm gonna lasso back up the very dangerous mortal coil of science. I love that. That's a good phrase for it because you guys don't know anything about Shakespeare because you're 14. But the mortal coil is what Shakespeare calls the whole life. Okay, so a transverse wave, the particles, because waves do happen in matter, they can happen in matter. Particles move at 90 degrees to the energy flow. And the other kind is longitudinal. Wait, in a longitudinal wave, the particles do move from place to place? No, they still just go back and forth. But in this one, the particles, the matter, if there is matter, move in the same direction as energy flow. So all of life, like the mortal coil, is a wave. Everything is always give and take, ebb and flow, back and forth, up and down. Nothing stays the same. Your book goes on to talk about interference, which are vocab words, and diffraction and refraction and reflection, which are vocab words. Basically, the last thing, because we're running out of time, from this, all energy disturbances are waves, we get the idea that waves can reflect, that waves can resonate, that waves can refract or diffract. Those things we'll have to talk about another time, but in essence, this is the boiled down principle of waves. All energy disturbances are waves, and the rest of it is just description of that. Do you have questions at all? I would say this is the main misconception to look out for. Energy flows in a wave, not matter.